if you wanted to find the area in here, this area between 1 and 4, the actual area that is under the curve and above the x-axis, we can use our old school pre-calc or geometry skills to do that. This shape is a trapezoid. So if I wanted to find the area of a trapezoid, then I know the area for a trapezoid is the average of the two heights. And how do I find an average? I add them and divide by 2. So I'd have like height 1 plus height 2 all over 2, and then times the width. So when I say to find the area using geometry, I literally mean old school, turn this into a shape, do what you would have done once upon a time when you were taking a geometry class. So when I look at this, if I'm trying to find the area of this trapezoid, well, the total width of that trapezoid down there is 3, because that's the distance from 1 to 4. So I've got a width of 3. And then here we have to do a little bit of work to figure out the heights. So when x equals 1, to figure out that height, I've got to plug 1 into my function. So when x equals 1, I'm looking at a y value of, so 2 times 1. Wow, it's 120, and I'm having trouble doing arithmetic. 2 times 1 is 2. Did you know that? Okay, so 2 plus 1, I'm looking at 3 for the height. And when I plug in 4, I'm going to get a height here of 9 from plugging 4 into the function. So in terms of my area, this would look like 3 plus 9 all over 2. So this is like me using geometry to find the actual area. 3 plus 9, that's 12, divided by 2, I'm down to 6. 6 times 3 is 18. I want everybody to keep that in mind for a second, because now we're going to do this problem 2 other ways. And one of them, we're going to loop back around to this 18. I need maybe more space on the board, but we'll get going. So now let's think about this in terms of a Riemann sum. We should probably decide how many rectangles we want to put in here, or how many sub-intervals we want. So this is the true, actual, correct, that is the area. So what we're going to do next, for no reason at all, is to approximate the area. We're not going to actually get that 18. We're just practicing the skill of approximating the area with a Riemann sum. So, new problem. If I wanted to approximate the area with a Riemann sum, let's say 4 rectangles, and let's use right-hand endpoints. So now, we're not talking geometry. We are instead going to go calculus style. If you are someone who is really good at memorizing formulas, then you can absolutely just memorize what this formula is going to look like. Since we've only done a couple of these, I'm going to work it out not just from the memorized formula, and I am instead going to think about, here's my interval. I need to break this into 4 equal pieces. Okay, maybe this part is a formula, but I know that the width of each of those pieces, my total interval width was 3, and I'm breaking that into 4 pieces. So the width of each piece is 3/4. Here's where life gets messy. I know, I chose fractions. We'll live. So we're starting off at an x value of 1. but we're going to use right-hand endpoints, meaning I'm going to take the right-hand side of each interval, and that is what will determine the height for that rectangle. I'm going to take the right-hand side of the interval, and that'll determine the height, the right-hand side of the interval to determine the height, and the right-hand side. So we're going to end up with a total of 4 rectangles here, and we're finding the area by adding up or taking the sum of the areas of those individual rectangles. In general, to find the area of a rectangle, I know I'm looking at a base times a height. And for each of these rectangles, the base of the rectangle or the width of that rectangle is 3/4. I'm going to write each of these out separately. So the area for my first rectangle would look like 3/4. That's the base. But then to get the height of that first rectangle, I need to know what's the x value that I'm plugging into the function. So we started out at 1, and then we moved over 3/4. So I could choose to think about that 1 as a 4/4, which means that when I moved over 3/4, I would be at 7/4. And then if I move another 3/4, I'll be at 10/4. And if I move another 3/4, I'll be at 13/4. And if I move 3 more fourths from 13/4, I get to 16/4, which is also known as 4. So it's going to work. So the area of my first rectangle would look like 3/4 because that's the base, and I'd get the height by taking 7/4 and plugging it into the function. So I'd have 2 times 7/4 plus 1. And then the area of my second rectangle would still have that base of 3/4, but now I'd be looking at 2 times 10/4 plus 1. Third rectangle, same deal, 3/4, 2 times, where am I at? We did 7/4, we did 10/4, so 13/4 plus 1. And my fourth rectangle, I'd have 3/4 times 2 times, oh, well, I guess we got to the edge. So we could write it as 16/4 or just write it as 4. You know, mathematicians like to be precise, but they also like to be efficient with their time. I sometimes call that lazy. But really it's about being efficient with their time and with what they're writing. So mathematicians said, well, if we're going to do this over and over and over again, wouldn't it be nice to have some succinct way to write all of this? Because really this area is going to be adding all of these together. So mathematicians came along and said, well, we could write this as the sum. They all have a base of 3/4 in this case. So I'd have a base of 3/4. And to describe what we're doing here to get the height, this 7/4 came from starting at 1 and moving 3/4 over. The 10/4 meant we started at 1 and moved 3/4 over twice. The 13/4 said we started at 1 and moved 3/4, 3/4, 3/4. And that 4, we started at 1 and moved 3/4, 3/4, 3/4, 3/4. So really, that height comes from 2 times 1 plus however many sets of 3/4 we've moved over. So we give it an indexing variable, I, multiply that by the 3/4. And this whole thing is my x star. It's saying this is what's acting like our x value that we're plugging in to the function. And then because we have 4 rectangles, my I is going to start at 1 and go to 4. So this notation is called a Riemann sum. If I summarize this Riemann sum for those of you that like formulas, our Riemann sum formula here has 2 pieces, right? We've got the width or the base of each of those rectangles. And that base piece is going to look like, we usually write it as b minus a over n, but really we're saying the final endpoint minus the initial point divided by n. So like what's the total width of the interval and then divided by n rectangles. And then the other piece here is coming from the height. And to get the height, we need to know what's our generic x value that we're, height, there we go. Coming from our kind of generic x value. So that generic x value, the textbook writes as x with a star and a subscript of I. And to get that generic x value, it's whatever I started at plus I, which is really just telling me how many times have I moved over, I of our delta x, I times delta x. So for us, this base piece of the b minus a over n is going to become 4 minus 1 over n. So that's matching up with this. And our height, we need to figure out what our like generic x value is. And that generic x value is going to look like 1, because that's our starting x value, plus I times our delta x, which was 3 over n. So our height comes from taking this x and plugging it into the formula. So we would have 2 times 1 plus 3i over n plus 1. Scoot both of these over a little bit. So our delta x was b minus a over n. Our xi star in general is a plus I times delta x. And specifically for this problem, that meant it was 1 plus I times 3 over n. So this is the area for our ith rectangle. And then we come in here and say we're going to add up all those rectangles from I equals 1 to n. And then the fancy calculus-y part, which I think I can squeeze in here. So we have the sum from I equals 1 to n is that we're going to take the limit as n approaches infinity. And that's going to be the very last thing we do with the problem. We're actually evaluating this Riemann sum, then we're going to have to do a whole bunch of algebra before we can take that limit. This is my pause. So if I take the sum from I equals 1 to 10 of the number 3, then notation-wise, this says when I equals 1, my function is 3. When I equals 2, my function is 3. When I equals 3, my function is 3. When when I equals 4, my function is 3. It's like the world's least interesting function. And we're going to go all the way up here to I equals 10. And my function will still be 3. How many 3's will I have? You could type it in the chat. You could show me on your fingers. Yes, I will indeed have 10. So we can turn, so I've got 10 of these 3's, which means the answer would be 10 times 3. So one of our rules is that if I take the sum from I equals 1 to n of a constant, then what I get is the constant times n. There's another important summation rule that we're going to need in a second. And I'm going to erase this. Still going to go from 1 to 10. But I'm going to make it slightly more interesting. And now my function is 3 times I. So if I write this out notation-wise, when I equals 1, this says my function is 3 times 1. And when I equals 2, my function is 3 times 2. And then when I is 3, I'm 3 times 3. And 3 times 4. All the way over here to 3 times 10. Well, one of the things that happens in writing that all the way out is each of these terms has a 3 in it, which means I could factor a 3 out of the whole thing. Or getting back to the summation notation, I can actually factor a 3 out of the entire sum and be left with, sorry, change colors up on you. I can factor the 3 out of the sum and have this go 1 to n of I. Oh, sorry, I meant 1 to 10. 10 n, they kind of run. 1 to 10 of I. And then this would look like 1 plus 2. This would look like, I lied, 3 times, because we factored that 3 out, 1 plus 2 plus 3, all the way up to 10. Once upon a time, maybe when you were a little kid, maybe on Friday, I don't know, someone talked to you about a shortcut for adding up the numbers. And we call these consecutive counting numbers. And there's a shortcut for adding up consecutive counting numbers. And it's pretty easy to show on a small sample like this. So I'm just going to write out I'm going to write out all the terms, plus 4, plus 5, plus 6, plus 7, plus 8, plus 9, plus 10. And the shortcut is, or at least sometimes people learn it this way. If I take the first number and the last number, they add up to 11. But 2 and 9 also add up to 11. And 3 and 8 also add up to 11, and 4 and 7 add up to 11, and 5 and 6 add up to 11. So adding up the numbers from 1 to 10 is the same as adding up 5 pairs of 11. That may not be that interesting to you, and it doesn't have to be, but here's a thing that you probably need to know and maybe memorize. So all of that was just to say that there are 3 summation rules that we really ought to add to our arsenal over here. If I take the sum from I equals 1 to n of a constant, we get c times n. The other rule is that if I have a constant times a function, I'm just going to call my function I, that's the same as the constant pulled out in front of the summation. And then this last one is that if I take the sum of I from I equals 1 to n. The formula for this is n times n plus 1 divided by 2. So I'm looking at the limit as n approaches infinity. And I've got the sum from I equals 1 to n, and I'm just going to start distributing things out. So right here, 4 minus 1 over n, that's 3 over n. So I've got 3 over n. And here inside of the bracket, if I distribute things out, I've got 2, plus when I distribute that to 6i over n, and then plus a 1. I'm really hoping, I'm going to try to squeeze it in here. We'll see how I do. So now if I take that 3 over n times 2, so I've got 6 over n plus 3 times 6, so that's 18i over n squared. Oh, I could have added the 2 plus 1 to get 3. And then I would have 3 times 3 over n, or 9 over n. Hold on tight, we're almost done. Just a couple more steps. This next step, the sum of the sums is the sum of some sums. That sounded terrible. All that really means is that if I'm adding up two pieces that are already added up, I can add them up separately. So I can take this and break this apart to say we're taking that sum over there plus this sum over here, 18i over n squared. Now it's time to use our summation rules. We don't know what n is because n is the number of rectangles that we're shoving in there. But with respect to I, our index variable, n is a constant. And since it's a constant, I know that when I add a constant from 1 to n, I get that constant times n. Then I'm going to move on to this next piece. With respect to I, since I is my index variable, that 18 over n squared, that whole piece is a constant. So I'm going to use this rule that says I can pull the constant out in front of the sum. So this piece right here can become 18 over n squared times the sum from I equals 1 to n of I. And because I'm short on board space, I'm going to magic this over. So I know that my sum from 1 to n of I works out to be n times n plus 1 over 2. And I'm going to pause and answer a question that came up in the chat first. And I can't quite tell which line the question is on, but I think it's this one and where this 9 over n came from. And I combined the 2 and the 1 to get 3. And then I multiplied the 3 over n in. I distributed the 3 over n in. So that's where my 9 over n came from. It's really 3 times 3 over n. And same kind of deal with the 18i over n squared. I'm taking this 3 over n and distributing it in. So I've got 3 times 6 is giving me that 18. My I is still on top, and the n times n, they're both on the bottom. So I rewrote that as n squared. So these two terms are coming from distributing that 3 over n in. So now we're to here. And I'm just going to give myself a little bit of space. And I think I can manage to squeeze it in. Oh, I really did not mean to erase the thing I just erased. What the heck? Okay. I had n times n plus 1 over 2, because that's what the sum of I is. That piece is getting multiplied by the 18 over n squared. And then this piece, that n over n, is going to give me a 1. So I'm going to end up with 9 plus all of that. Now this looks terrible, but we're taking the limit as n approaches infinity. And the good news is that typically by 17b, no one cares if you're showing a ton of work on that limit. You just have to be able to find the correct answer. So when we get to this point on all of our Riemann sums, we're hoping that whatever happens over here, I have the same power of n on the top and the bottom, so that we can use that cool limit rule that we all remember from 17a, that if you take the limit as n approaches infinity and you have the same powers on the top and the bottom, that you look at the coefficients. So on the top here, if I distribute that out, I'd have 18n squared. And on the bottom, I have 2n squared. Technically on the top, I have 18n squared plus 18n. But when we take the limit, we're only going to look at those largest powers, which means this thing just turned into, in the limit, 18 over 2, which is also 9. And 9 plus 9, very anticlimactically, is 18. Suppose that I have some function f of t. And to relate this to Gorski's first lecture, maybe this is some kind of velocity function. So I'm moving along and my f of t is telling me the velocity. Well, if I care about this shaded part of the graph from a to x, and remember notation-wise, because this is f as a function of t, that means this is really the t-axis here. And if I think about this area, this area is a function of x, because depending on where I draw this vertical line, I'm either going to have less area or more area. So the area is a function of x, even though this picture is a function of t. Now to get that area, and thinking back to what we talked about Friday, if I were to draw some arbitrary cross-section in here at a particular value, then this arbitrary cross-section has a base and a height. And its base is some little bit of dt. Why dt? Because I'm on the t-axis. And the height I would get by plugging it into the function, which means that if I think about that arbitrary cross-section as a height times a base, that would look like f of t times dt. And then we'd come in here and add them up. An addition problem is also called a sum, and sum starts with s. And I would be adding these up as far to the left as a and as far to the right as x. So this is our notation for a definite integral. So this definite integral represents that area. Now, suppose just for fun, or actually because I already know where we're going with this, that I this, but I actually, oops, I didn't mean to. I really wanted to come all the way over here to x plus h. And I really wanted the area right here between x and x plus h. So this actual shaded area, so my red shaded area, trying to keep track of my colors here, but the actual shaded area would be f of x plus h minus f of x. And if anyone in their head is going, oh no, not back to 17a again. Yes, back to 17a again. You know where we're going with this. So that's my actual shaded area. But if we just approximated that shaded area, then we could approximate that shaded area and say that's approximately the same as pretending it's a rectangle, where the base is the distance from x plus h back to x. So the base was x plus h minus x, and the height I would get by plugging x into our function. So they're not totally equal, but they're approximately equal. The shaded region versus this rectangle. But if I look at this and I simplify this part, x plus h minus x is h, and then you're going to look at that and go, wait, if we divide that h over, we sure know what this is. We know what this is as long as we put a limit out in front of it. And if I put that limit out in front of it, the limit we care about is the limit as h approaches 0. And if we take that limit as h approaches 0, this doesn't just become approximate, it becomes exact. What the heck does that mean? That means that we have a relationship between the thing that's inside and the area. And that relationship is whatever is inside of our integrand, whatever function is in here, it's somebody's derivative. So the fundamental theorem of calculus says, instead of doing all that Riemann sum stuff, if I wanted to calculate, let me get rid of my picture for a second. If I wanted to figure out the area from 1 to 4 of 2x plus 1, all I actually have to do is find the antiderivative. What's the antiderivative of 2x? Well, it's got to be x squared because that's whose derivative is 2x. And the antiderivative of 1 is going to be x. And I don't have time to prove the second half of the fundamental theorem of calculus, so this is going to have to wait for Wednesday. But the second half of the fundamental theorem of calculus says plug in the last endpoint and subtract off plugging in the first. So if I plugged in the last endpoint, I'd have 4 squared plus 4. If I subtracted off plugging in the first, I'd have 1 squared plus 1. And what do you know? I am looking at 16 plus, right, 4 squared, that's 16. 16 plus 4 is 20, minus 2, and it's 18, and bam, and that's actually how we're going to get the 18 from here on out, is from using the fundamental theorem of calculus.